Good morning, mechanics of material students. Wanted to review a very important subject from statics that some of you may need a refresher on. So one of the basic tenets of statics is if it's not moving, it's in equilibrium, which means that you can treat it as a rigid body. You can treat any member as a rigid body. You can treat any body as a rigid body and separate them from the rest of the universe by drawing a circle around it and saying, all right, this piece, since it's not moving, is a rigid body and I can treat it as such. Anyway, that's the basis of the method of sections, which we will use for much of our analysis. So, at any rate, the method of sections began in the truss section, or at least it was first mentioned there. So, let's say that we have this truss. Well, this is one of our homework ones here, and let's say we wanted to find out the force inside this truss and one of the members. Well, we could do the method of joints and step from here to here to here to here and find out what's going on inside the truss, or we can try the method of sections. The method of sections says that I can draw a little section any place and then analyze it as such. So anyway, I want to find the force in member BC, and I'm going to do that by drawing the method of sections there. And so I've repeated the section down here. And let's say that what we're going to do is we're going to assume that the forces are in tension. They may not be in tension, but we're going to assume they're in tension. And in order to find out the force in BC, I can just sum the moments about G. So let's sum the moments about G equals 0, and I do that. Again, what I'm saying is that because the truss was in section, or was in equilibrium, then obviously this section is in equilibrium. So sum of the moments about G, and then I got 1,000 times this lever arm times 2. And that force goes through G, that force goes through G, but this force, this is force BC, that one has this lever arm, which is 2 meters over there. So that is minus BC times 2 meters, and that's equal to 0. So BC is equal to 1,000. And I drew the arrow as a tension member. It came up as a positive number, so that says that I drew the arrow correctly. That is in tension. Okay, pretty easy to do. Let's find the force in GF. So I'll use the same section for that. And I can move it down here. Keep doing that and that and that. Let's sum the moments about a point off the body here, which is point C. And I can find the force in GF, which is right here, so let's do that. Point C is way out here, so here's my lever arm, so sum the moments about C equals 0, so I got 1,000. In this case it's times 4, and then plus GF, and this lever arm here is 2 equals 0, so GF is equal to negative 2,000. Now, negative 2,000, I drew it as a tension member, which means it's actually, the arrow is going the wrong way, so it's actually GF is equal to 2,000 compression. And that should be the answer. And that compares with, let's see, where is my, oh yeah, here's my MD Solids work that we did for the homework. And you can see that, I don't know if you can see that, but right here, yeah, it looks like that one is 1,000 tension and there is 2,000 compression. So anyway, hope that convinces you that the method of sections makes some sense. Let's move on to a different piece. And now you'll recognize this piece from the homework, or from the pre-quiz, I'm sorry. This is a frame and machine problem. And we're going to use the method of sections to solve this. But anyway, if you draw a free body diagram of the whole thing, looks like that. And there'll be some pushing force here, reaction force there, some AY, some AX, some FY, and some FX. Let me draw them both positive. I guess it doesn't matter. FX, we'll draw it like that. But anyway, if we do that and try to solve this by summing the moments about A, we would have this 200 times 0.3, and that would be negative, plus E times 0.6 minus Fy times 1.2 equals 0. I got two unknowns there, that's not going to work. So let's sum of the forces in the x direction. So we have plus 200 minus E, those are those two forces. I'll say minus AX minus FX equals 0. Still got two unknowns. Actually, I just introduced two new unknowns, so I got four unknowns. Let's try F in the y direction equals 0. So I'll say you got plus AY minus FY equals 0. So introduced yet another unknown. So I got three equations, five unknowns. Nothing's going to happen there unless I break it apart. So we use the method of sections to break it apart. And the way we do that is that we draw one piece there, another piece there, and another piece here. Keep our same pushing force, the same reaction forces. And here we have to recognize that that one is a two-force member, which means that it's either in tension or compression. I'm just going to assume that it's in compression here, and those forces have to be transferred equal opposite to the members, other members at their joints. And then we'll have our E here, and I'll draw my Fy and Fx in the same way I did before. But at any rate, once you break it apart, then you can resolve things, because you get some moments about here to find that easily. Once I find that, I obviously know that. Then once I know that, I can sum moments about here to find that. So, pretty easy to do once you break it apart using the method of sections. Method of sections on this truss as well. Now you can use the method of joints, which is obviously valid, but the method of sections is what I'm trying to illustrate here. So let's use the method of sections on this piece here. And let's draw a little section like that. And we can draw that as a separate function. And the first part of it was 300 acting alone, so I'm going to put 300 there. Because these trusses are two-force members, we know that they're only in tension or compression, so let's just draw that guy in tension and this guy in tension and see what we got. Because there are components here, you got this is AB, you got an AB in the y direction and an AB in the x direction. Because we know those exist and there aren't any other y forces in here, we can conclude that AB equals 0, which indeed it was, and you recognize that from the homework. So that says that this one is BC. So BC is carrying the entire load of this 300. Method of sections. So again, let's do that to discover what happened with the other force. The other problem was 900 acting alone. Well, again, we'll draw this in tension and this one in tension and see what we get. Because there is a y force here, this is AB, ABY and ABX, and I think those are all the forces in our drawing, so in our problem. So since this is a y force, that has to be equal to that y force, And because there's a relationship, because this is now a this is a two-force member, we know there's a relationship related to the tangent of theta here, that ABX is related to ABY, and then we can say that ABX is equal to BC. Some of the forces in the x direction, some of the forces in the y direction. Anyway, just to illustrate the method of sections in a simple truss. We also use the method of sections when we resolve beams like this for finding shear and moment. So I think the problem was find the shear and moment at a particular place. So the way we do that is once we find out the reactions that we can, then we draw a little separate section. So we'll draw the section of, I'll just do it right here, of that piece of it, like that. And again, because this was a fixed support, it had a X and a Y and a moment, and we knew that there was some reaction there from the little triangle that was left. Now, here again, we should draw positive shear, positive moment, and positive normal force. We'll go through this some more when we get to shear and moment, but the point I'm trying to illustrate is that's the method of sections, which means that this piece now is just as much in equilibrium as the entire body. All right, so let's talk about how we use the method of sections then to understand how to resolve these internal forces, because I think that's where some of the confusion was. All right, so let's say we got three forces acting on a beam that has a fixed support. So I'm going to draw a reaction over here of A. Draw that reaction at A right there. And let's put some numeric values in here because I think that sometimes is easier. So I'm going to call P1 equal to 10, this one equal to 20, and this one equal to 30. I can do some of the forces in the x direction. Treat the whole thing as rigid. Some of the forces in the x direction should have to be equal to 0. So, and let's call that my positive direction, easily. So I'm going to say that minus A, P is going that way, so plus 10. P2 is going that way, so minus 20. Minus 30 has to be equal to 0. Do that, and I find that A is equal to 20. And it's a positive number, which means I drew my arrow correctly. So let's just leave it like that. Now we use the method of sections now to find out what the force is in any particular piece. It's not, yeah, so anyway, so find the force in there. So let's draw a little section right like there. Now this force, or this section, is very close to this, but not right on the point of application of the force. And the reason is because then you have to decide, well, do I put the force on, on this side or on that side? So I like to draw the force right inside here if I want to find out what's going on between A and B. So let's draw the little section there, and here is my section AB. I know that I got 20 over here. Because this section is now in equilibrium, I know that whatever happens over here has to be equal to 20. Since I've already resolved for that 20, I know that the sum of those things has to be equal to 20. So let's just make sure it is. So I've got a P1, a P2, and a P3. So I'm going to say plus 10, minus 20, and minus 30. Did I do that right? Oh man, I did not do it right. I know what I did. I changed my drawing here. So, well, rather than start completely over on this video, I'm just going to change it right here and call that equal to plus 30, because that's what I had done on my drawing. On the next one I used it is minus 30, but here I want to call it, if I can get my eraser to work here. Alright, here. Sorry about that. Let's just keep that as like that, and that's plus 30. So now I'll go back and correct that. There we go. There we go. Now I should be straight. So here I've got plus 10, minus 20, plus 30. All right, so now back to the section. I got AB as a section. I got minus 20 going this way, or 20 positive, I guess positive 20 going in that direction. And then I got plus 10, minus 20, plus 30, and indeed if you add those things up, those equal 20. So I can just look at that, say, and I can say, well, if that's 20 going that way, that's 20, then AB is 20 in tension. Okay, how about BC? Well, we can draw two little sections now, one on each side of that. So let's draw little sections of BC. And I know whatever happens over there has to be equal to whatever happens over there because that section is in equilibrium, so let's add them up. So I got, on this side, I got a minus 20 and a positive 10. So I'm going to say this is 20 and 10. Whatever happens on this side has to be equal to that. So on this side I've got a 20 going that way from this guy and a positive 30. And again, you add those things up and I got 20 and 10, 20 and 30, so that means I have a net 10 going that way and a net 10 going that way, so I will say that BC is equal to 10 in tension. Alright, then the last one is very easy because we can know that 30 is over here. I can say that this is 30, and by observation I can say that CD is equal to 30 in tension. Alright, then of course to do your deltas, you just say, well, once I know the force, I can do my deltas as PL over AE. Alright, let me just do one more here. And here I've got the force back to the way it looked in the drawing. And I've changed the values just a little bit. So I got, well, no, I guess I didn't change the values, but I got this 10 and this 20 and this 30, but it's going in this direction. So let's do some of the forces in the X equals 0. Now this way, let me just draw that one as A going positive, and I'm going to draw that as my positive direction. So here I go plus A, plus P1, so plus 10, minus 20, minus 30 equals 0. So here, A is equal to, this is, A is equal to 40. And I got a positive number, which means it agreed with the arrow that I was drawing. Now the other way to do this is not to have to draw an entire section, but just to say, I'm just going to draw a single section, not a section of the drawing, but just basically a squiggly line saying, again, this is a piece that has to be in, or this is a line, I guess, that has to be in equilibrium. So what I can say here is this line, which represents what's happening on the inside of AB, we're going to have an A here and going to have whatever's happening over here. So I'll say that it is plus 10 from P1, minus 20, and minus 30, and we know that A is equal to 40, and indeed that does balance. 40, 50 minus 10 going this way, so I got a net 40 going this way, and a net 40 going this way, so that says that AB is equal to 40 in compression. Alright, I will leave it there. You can continue on and do the same thing with BC and CD, and note that BC is equal to 50 compression, and then CD, you can observe that because that's pushing on that, the whole thing has to be CD is equal to 30 compression. Okay? Alright, I hope that is somewhat helpful in using the method of sections. Alright.